Okay, guys, so welcome to the second class. So today we're going to do the last part of the chapter 4 with the generalized axiom of revealed preference, finally, right? And we stated and we did a little bit of the proof during the summer, but there was some details I wanted to do. And yeah, we're gonna complete it today. And with this, we're done with this chapter. Okay. So remember that in general, the previous theorem that we studied in the previous class about the weak axiom of revealed preference, the characterization theorem with rationalizability or rationalization of the choice correspondence, is only works when you have rich data sets, so tuples and tripletons, okay? So one thing we did in the summer was we did a nice example showing that there were data sets, right, that could fail to be rationalizable but satisfy warp, okay? And that happened basically because you have a less than rich data set. Understood? So now, given that, we need a more powerful condition that characterizes fully rationality when you have a data set that may not be rich. So why do we care about this motivation? Well, in general, you have an experimenter, right? An experimenter may not have the money or the time or the resources, right, to run all possible binary pairwise data sets and tripletons. So imagine you are hired by Spotify, right? And you want to know, you want to recover the preference of the consumers. Can you really force them to compare all binary songs or even artists, right? Can you? Not really, right? So you're always going to have a subset of menus due to your limited resources, and you're going to see choices from it, okay? So we want a condition that is able to allow us to recover preferences, and test also is able to characterize rationality, and hence become a test of rationality for general data sets less than rich. Such an axiom is called the generalized axiom of revealed preference, or the GARP. Okay, so from now on, I'm gonna refer to this as the GARP. So we say that a data set satisfies GARP if for any pair of alternatives x and y, such that x is, remember the symbol with a star, this is indirectly revealed preferred to y. So I'm writing it also in words. So remember, there is a chain of alternatives such that x is directly preferred to x1, and then ... directly revealed preferred to xn, and then finally to y. So indirectly, you infer that x is better than y. So we discussed this before, right? So this is interpolation of preferences. And then once you observe this indirect revelation, then it must not be the case that y is directly and strictly revealed preferred to x, okay? So can you see, first of all, that this is this implies the warp, right? So can someone explain me why this implies the weak axiom? Who will do it? Else I will ask. Xiao, can you hear me?
Yeah, I can hear you.
Yes, can you tell me why the GARP implies the warp?
So I think the definition is quite similar, except for the fact that GARP like kind of adds the indirect relation between x and y, but the intuition is kind of the same. So if you know that x is revealedly preferred to y, then y cannot be like directly revealed preferred to x. So
yeah, so
it's kind of the same.
I think you have the correct intuition, but that's part of this class, right? So let's try to do formal, okay? So I want to establish formally that GARP implies warp. So this is a logical statement. So what does it mean? So basically, I have to show that if I start from the premise of warp, what is the premise of warp? That x is directly preferred to y, right? Then, using GARP, I will conclude the conclusion of warp, that is that it cannot be that y is directly will refer to x, right? So you can see basically that the fact that x indirectly will refer to y, right, is a more general revealed preference. In fact, this relation, this revealed preference, the indirect revealed preference includes, is a superset of the direct revealed preference, right? Do you agree? Yeah, so once you observe that, then the proof has been established formally, because you basically realize that if you observe the premise of the weak axiom that x is directly referred to y by GARP, right, then it cannot be that y is directly referred to x, right? So that's the formal proof. And yes, Xiao was very, very close, but you have to train yourself on trying to be more formal on the arguments. Great. So GARP is more general than the weak axiom. So GARP implies the weak axiom, but the weak axiom does not imply GARP. However, we haven't formally established that it's not the other way around, so that WARP does not imply GARP. So remember this example I generated in the summer, right? You remember that I did this, basically this choice correspondence, right? That fails WARP, but satisfies the weak axiom. So fails GARP, sorry. So you have basically a choice correspondence out of A and B equal to A, out of BC equal to B, and out of AC equal to C. Why this fails the generalized axiom? Because you have that A is strictly referred to B, and then strictly referred to C, but C is strictly referred to A, right? So this obviously fails the GARP, but you can see that WARP is satisfied, right? Because WARP is only concerned for pairwise comparisons, right? And here there is a chain involving 3 items. Everyone agrees? Okay, so this is important. And now, why do we care about the GARP, right? So basically, I'm gonna read this extension theorem that I added from the summer, so it's more clear on the text. So this is the new version of the notes that you can access through GitHub, right? Remember that if you already are using GitHub, you can see all the updates I'm doing. So this small extension theorem is from the book of Revealed Preference of Chambers and Echenique. You don't need a book, so you just need the notes. So the theorem says there is a complete and transitive preference relation, right? That is an extension of any preference relation. For now, I'm gonna call it R, right? So you can replace the symbol R for the preference relation with a star. This is irrelevant. I just want you to not be confused by the notation. So I'm using any preference relation that I'm gonna symbolize by R. Even only R satisfies the GARP. So remember, what does it mean to satisfy the GARP? Basically, I use the definition here, right? That I just gave to you. And instead of having the symbol with a star, I replace it by R. So again, so even if you want to be, sometimes changing symbols in math is good to really understand the concepts, but to avoid confusion, let's do it even this way, right? So it's even clear what's happening. So now, one important thing, I'm using this word extension. And what is an extension, basically? An extension is a binary relation that has the property that basically it will respect, right, the strict part and the weak part. So in other words, the revealed preference relation that we have here with the sum of someone with the star is a subset of the complete and transitive preference relation, which is a rational preference relation. But not only that, also the strict part is a subset of the strict part of the rational preference relation. So this may be a little bit confusing, so I'm going to clarify a little bit more, just that we are in the same page. I'm just changing the symbols right now because I realized this may cause some confusion. So I just went back to the original revealed preference notation. So let me tell you what it means. Basically, another way to write the things I wrote just a second ago is the following. So this is equivalent to saying that if X is reveal prefer strictly to Y, right? Then it has to be that in the underlying preference relation, which is an extension of the observed reveal preference relation, X also is preferred to Y. And if you have that X is weakly reveal preferred to Y, then X is S is preferred to Y. So here you have two preference relations. What is the difference between the both of the symbol without the star and the symbol with a star? The symbol with a star is the one that you get from the data set, is the reveal preference relation. This one in particular is an incomplete preference relation, right? Why is typically incomplete? Because you have data sets that are not rich enough such that you never get the full revelation of all preference binary comparisons. Do you understand? So imagine you have the 3 items. I only have money for running 2 menus. It will never be complete, right? So the preference with a star is incomplete, typically. The preference without a star, that's the extension, right? That's the interpolated model, the one that is defined over all possible binary comparisons. And that one is complete and transitive. Do you understand? So the one without the star is the ideal, underlying rational preference relation. The one with a star is the one coming from the data. Understood? Any questions here? This is a kind of interesting, hard concept. So I'm happy to stop here. So
yeah,
questions?
I have a question regarding that. So it would be a case, for example, in the example that you provided, I think it was the last lecture about Spotify doing like comparison between your choices, so that they can compare every possible pair. Is that the case? It's more or less like that. Oh.
Yeah, exactly. So if you were in an ideal world where you could get all possible binary comparisons, right, and all tripletons, then your direct reveal preference relation, right? In fact, the reveal preference relation will be complete, right? That's the proof that we did the last lecture, as Martin says. In real life, you never get all binary comparisons, right? So typically the reveal preference relation, the one with the star, is incomplete, okay? And that's the point here. So I'm giving you now a general theorem telling you, you can, whenever the preference relation, the reveal preference relation is incomplete, so you weren't able to run the whole experiment with all binary comparisons, you can still interpolate, right? And you can always interpolate as long as the reveal preference relation satisfies the GARP. Remember that this is the condition so that I can interpolate and learn preferences, right? If you fail GARP, there is no way to do it. Do you understand?
Sorry, Professor, I'm a bit lost in Lemma 2.
Yep.
So what is R?
Yeah. Sorry. So originally, right, I wrote it with a different symbol. So to understand that this extension theorem works for any binary relation that satisfies the GARP. But you can think in this lecture, to avoid confusions, and that's why I changed the symbol right now, that this symbol that I substitute, the R for the preference symbol with a star, right, is for all purposes for this class, the reveal preference relation that we are working with, okay? Is that clear, Irina? So this is a mathematical result that can be done for any relation, hence the previous symbol. But for the purpose of this class, it's fine to think of this as the reveal preference relation, okay?
So, Professor, so you're saying for us to predict the behavior, we need at least the GARP at least should hold, right?
Perfect. That's a perfect way to say it. So actually, let's go back to example 18 to solidify this point Irina is raising. So in example 18, I gave you this example that you have 4 alternatives, A, B, C, D, E. Now I basically propose the menus A, B, B, D, A, B, right? And then I propose the choices. Out of A, B, this consumer chooses A. Out of B, D, this consumer chooses B. Out of A, D, this consumer chooses A. From this, I get my reveal preference information, right? So A is directly and strictly reveal preferred to B. B is directly and strictly reveal preferred to D. And finally, right, I don't have, I never observed, right, that D is directly referred to A. This doesn't happen. So hence GARP holds. So, okay, so GARP holds, that's great. That's our starting point. Now, let's see now how can I predict, preferences from this guy. So my preference relation now, I will propose a preference relation that says A is better than B, better than D. Now, what happens here? Look, that a true preference relation, the one without the star, should be a ranking over all alternatives. So here, what I'm missing is the E alternative, right? So in order to predict what's going to happen with E, I need to basically extend the original indirect preference relation with a star to the general model that is complete and transitive. Do you understand what I'm trying to do? So I'm trying to create a complete and transitive extension, right, of the indirect revealed preference relation. So now with that in hand, look that I can basically put the item that is not ranked in the data anywhere. In particular, I can put it at the beginning. E is better than A, better than B, better than D. Okay. And then now, important question. Is this the only way I can do it? No, right? So look at the extension theorem I'm giving you. This is only saying that there exists some complete and transitive preference relation that can extend the indirect preference relation, okay? So in a way, in this particular data, you are learning how the alternatives A, B, and D behave, and you can predict that whenever you put together A and D, A is going to be picked, right? That's the prediction part that Irina said. However, sometimes you cannot make predictions for some alternatives that you don't have information about, like E. E, for instance, can be at the beginning or can be at the end, right? Or you can actually put it somewhere in the middle, right? Because there is no information about E. And all of these complete and transitive rankings still work, okay? Now, important thing here, if GARP fail, you cannot do this, right? So now the theorem enters in full force. If GARP fails, there is no complete and transitive preference relation that can extend this data. So you cannot make predictions. Is that clear?
Yeah, so in the example you provided, given that GARP holds, so in that case, even if Spotify cannot make all the comparison between the all possible pairs that could alternatives, they could still work as if they had those observed choices.
Exactly.
Okay.
That's perfect. That's a perfect way to see it. Okay, great. Okay. So now, and that's the whole point of this, right? So as you can see, this exercise we're doing is very similar to an econometric exercise, right? So you get from data and you're trying to feed a model, you're trying to recover some hidden parameter, right? The only difference here is that we have non-parametric objects. So we're recovering preferences without parameters, right? We're just recovering the ranking directly from the data, okay? And the way you are able to do it is if GARP holds. If GARP fails, you're done. So now let's formalize that statement. And this is the equivalence or characterization theorem. Theorem 7. This concludes the chapter and is the most important one of this chapter. So the following are equivalent. So when I say the following statements are equivalent, it means that 1 and 2 are logically equivalent. 1 implies 2 and 2 implies 1. First statement, the choice structure, so a data set that we discussed in the previous lecture, satisfies the GARP, okay? So you know that basically that means that the revealed preference relation that I get from this data satisfies GARP, okay? So we know that, we understand it. This is equivalent to the data set, the choice structure data set, being able to be weakly rationalized by a rational preference relation that is complete and transitive, of course. So remember that the previous class, I told you what is weakly rationalized. So it means basically that the choice correspondence is a subset of the set of maximizers. So I put this definition right here with equality when we say it rationalizes it. And at the end, I also added the weakly rationalization somewhere in the notes yesterday. Okay, now let's prove the first part of the equivalence theorem. So whenever you see an equivalence theorem, what I will do is I basically will show that statement 1 implies a statement 2, right? And then I will show that 2 implies 1. So in equivalence theorem, we basically have a two-way street, right? A two-way street. So basically 1 implies 2 and 2 implies 1, okay? So now sufficiency. First, define the indirect preference relation as the asymmetric part of the revealed preference relation, such that, so right now I want to show that the satisficing GARP implies that you can be rationalized by a preference relation. So this is the most important part, because basically we can generate a preference relation that is complete and transitive, right? That rationalizes the data. So this is called the sufficiency, and is the hardest part of this theorem. Now, remember.
Sorry, so here you're like proving, like, as if we're saying it's if and only if, correct? Isn't
Perfect.
it? This
Yes,
kind of,
yes.
yeah, okay.
Is exactly that. So, you know, there are different ways to introduce this kind of statements. Irina is giving you the one of the classical ways. So I can say as in the same way, the choice structure satisfies GARP if and only if it can be weakly rationalized by a preference relation, right? That will be equivalent to this thing, okay? So this is just more orderly for the eyes, and in revealed preference is how we are used to write it, okay? So this is just our aesthetics, right? Sufficiency. First, remember that I defined this symbol of a strict preference relation with a star as the asymmetric part of the indirect preference relation star, okay? Now, such that if A is strictly revealed preferred to B, even only A is indirectly revealed preferred to B, and it cannot happen that B is strictly preferred to A. So this is, you know, a classical definition of the asymmetric part. This is the strict preference, revealed preference relation. Nothing new here. Now, GARP, if you the condition that we impose, GARP implies that the direct preference relation is a subset of the strict part of the indirect preference relation. Do you understand why? So this is very easy, right? So basically, if you have that the direct and strictly revealed prefer, what does it mean? It means that the item A is directly and strictly revealed preferred to B whenever A is chosen, right? And B is not chosen. That part you remember, right? That is the revealed relation with a superscript D, with a strictness. A strict means that B is not chosen, right? So that you remember. Now, if that happens, then it has to be that it is also indirectly and strictly revealed preferred to B. That's obvious, right? Because the indirect revelation is a more general case of direct revelation, right? So you agree with this statement. Now, notice as well that the weak part of the indirect revelation is in the transitive closure of the direct preference relation. So this part of the transitive closure basically is the lemma I just provided. So this is by the lemma below, right, of Echenique-Chambers. So in other words, right, the fact that the indirect preference relation, right, basically is satisfies GARP, right? And also we know that GARP implies the weak axiom. Basically, it means by the extension lemma that if you take the closure or the extension of the direct preference relation, you will get basically the fact that the indirect preference relation belongs to the closure of the direct preference relation. So, and this is essentially an analogous argument to the one that I just made for the strict part. Now, and here is basically the part of the proposition 1 in chapter 1 that I move it and make it a lemma. So now we can just use the new one. So instead of using this thing, I'm going to replace it by the lemma below Echenique-Chambers, because now we have this updated lemma that I just changed in the notes here to claim that there exists a complete and transitive preference relation, right? Such that if X is indirectly preferred to Y, it implies that X is preferred to Y. in the constructed preference relation that is complete and transitive. Remember, when we're talking about extensions, it means completing them. It means being able to extend them, to interpolate. And also, importantly, if X is strictly directly preferred to Y, it implies that X is preferred to Y in the extension. Okay, that's the work we did in the Echenique-Chambers lemma. Okay, now, so one important thing that you have to observe, remember that in the previous proof, in the previous lecture with the weak axiom, we use a direct construction, right? So we just equated the rational relation, that is complete and transitive, with the revealed preference relation. Here instead, because the indirect preference relation is no longer complete, because you don't have rich data, right? The data is not rich, you don't have all binary comparisons. Now you need to do an existential claim, right? So this proof here is relying on a non-constructive step, okay? So we're not building physically the underlying complete and transitive preference relation. We instead are invoking this lemma by Chambers and Echenique, right? So this is a non-constructive step, okay? So this is a type of proof that doesn't build physically the preference relation, but rather invokes an extension theorem, okay? So this is important that you notice, right? Because here you're basically taking and what is called the axiom of choice. So in mathematics are divided philosophically into two branches, right? Constructive mathematics and the other that is not constructive. Whenever you say, by the way, by this theorem, there exists an object, right? That is not constructive mathematics. And all of that is based on something that is called the axiom of choice, okay? So you can Google it, Wikipedia is kind of fun to see the two differences in terms of math, but this is how we do it here. We do it with a non-constructive approach. And basically we're assuming, we're not assuming, we are using basically the axiom of choice. And in fact, a special case of the axiom of choice, that is the extension theorem in Chambers and Echenique, to ensure that there is an extension of the indirect preference relation to a complete and transitive one. Now, one thing that you have to realize is that this sounds more ethereal than it actually is. So for finite data, the existence of such extension is trivial. As you can see, whenever you satisfy GARP, right, these things are acyclic in the sense that there is no loops. So it's never the case that the beginning of the chain of revelation, right, is basically tied together to the end of the chain. In this case, you have that A is revealed preferred to D, but D cannot be revealed preferred to A. So what you're doing with GARP is you are breaking loops, right? So loops are disallowed. You cannot have loops, okay? So this is GARP. If that's the case, then you can see that for finite choices like A, B, C, and E, it's very trivial to construct an extension that is complete, that basically satisfies complete and transitivity, right? So basically, a cyclicity is the incomplete version of transitivity, if you want. So you can add additional items to the relation to make it complete while respecting the cyclicity of the GARP. So what I'm saying is that for finite data, you can actually physically build extensions, such as in example 18. But why do we use a complicated extension theorem, such as the one in lemma 2? Because we're dealing with a theory that is general enough, not only for finite choices, but also for infinite choices, like the one we discussed in the previous lecture with the fractional trading. So the whole Euclidean space, right? So in those cases, constructing an extension with a complete and transitive relation of very large indirect preference relations in a complex topological space, you need heavier math, right? Hence the extension lemma, okay? But in other words, you have to understand this in two levels. The intuition should come for the finite case. So I think example 18 is the way to go, right? So we're not doing anything magical, really. We're just interpolating the incomplete relation to a complete one that satisfies transitivity. And transitivity can only survive if GARP holds in incomplete data, right? Do you understand? So GARP is the condition that allows me to extend and complete the observed direct preference relation, okay? Now, for of course, more complex setups, we use this extension lemma in Echenique chambers. But of course, the intuition gets weirder and heavier. So it's fine if you are still having issues understanding this, okay? But again, ask me at the end of the proof again. Yeah, Martin, go ahead. So let's do it.
Could you overcome the problem of, I don't know if it is a problem or not, that the proof is non-constructive by stating the whole theorem again in the proof?
No, so basically you cannot get around this issue, right? Basically, the only way to prove this GARP condition in this level of generality, right, with complete abstract choice sets and without further structure on the space of choices, is basically by using this Zorn lemma. Now, what I'm going to tell you.
No, I agree, but this problem that I resort to this lemma that is, I don't know, written down anywhere else, but could you overcome this problem by stating the whole lemma again in the proof so that it is explicit?
I mean, that's just a stylistic point, right? So, but it's not going to eliminate the fact that you need the extension lemma.
No, for sure.
Yeah. Okay.
Yeah.
Now, important point for Martin and the rest. So actually, when you have more structure on the choice set, for instance, when we're going to move to the world of linear budgets, we can do actually a constructive proof. It's a very famous one, and we will do it at a time. And this is called the Afriyat's theorem by Sidney Afriyat. And we will do it, in the next chapter, okay? But not right now. So in other words, if you add more structure to the choice set, you can do constructive proofs, but at this level of generality, this is the best proof you have, okay? So great, let's keep going. And now, right? The important thing is that we use the extension lemma to claim that there exists, right? Non-constructive, a complete and transitive preference relation such that basically is a superset of the indirect preference relation, meaning that if X is indirectly referred to Y, this implies that in the generated by the lemma preference relation without the star, X is also preferred to Y. And also, importantly, it respects the strict part, okay? So if X is directly and strictly preferred to Y, it also implies that in the extension preference, X is strictly preferred to Y, okay? Now, this implies basically that if X belongs to the choice correspondence for some menu A, this implies, of course, that X is directly preferred to Y for any Y that belongs to the menu. And this implies, and that's the nice thing, that X also is ranked above Y in the extension preference for all Y, meaning, right, that whatever you observe in the choice set will be a subset of the set of maximizers, meaning that this is, of course, a weakly rationalization of the choice correspondence. Also, imagine X is not in C, right? This implies there is, because of non-emptiness is a big assumption here. There exists a Y such that Y is strictly and directly will prefer to X, right? Why? Because X is not big, right? The choice correspondence is not empty, so there is one Y, okay? And Y has to be directly and strictly preferred to X. So combination of two things, non-emptiness, right? And basically the fact that X is not there. So this implies that Y is above X, right? And not X implies Y. So together, this implies that these two things are the same. Hence, the data is equal to the set of maximizers. Okay, agree? So this is basically cleaning the house, but very simple. Now, let's do the easy part of the theorem, which is called necessity. Necessity now says that if you have a data set that is weakly rationalized by a preference relation that is complete and transitive, you must satisfy GARP, right? So that means that GARP is also a testable implication of rationality, okay? So this is necessity. 2 implies 1. So I'm going to prove it by contradiction. So this proof is easy. Assume toward contradiction that GARP fails, and the data set is rationalized by some complete and transitive preference relation of this symbol. In other words, X is indirectly preferred to Y, and then this Y is directly and strictly preferred to X for any pair X and Y. If that happens, that's a violation of GARP, okay? Because the proof is towards contradiction, that's my assumption. But because this is remember that my assumption is also that the choice correspondence comes from maximizing a preference relation. So because of maximization, it follows that X is better than Y, and also that Y is strictly better than X. But that implies that there is a sequence of alternatives, X1, X2, Xn, such that X is really preferred to X1, Xn, then Xn is better than Y, and then Y finally is strictly preferred to X. But this is a violation of transitivity, right? Obviously. And this means basically that the underlying preference relation is not complete, and mainly it's not transitive. Completeness here doesn't play a role, actually. It's mainly that a violation of transitivity. So as you can see, there is this connection between transitivity and GARP, right? It's not the same, as I told you. GARP is missing completeness, right? It's a condition that doesn't require completeness, right? Transitivity is combined with completeness to be able to imply GARP, okay? And this is what is happening here in necessity. So now, what is the take-home message? So let's go back to the statement of the theorem. And again, in this characterization theorem, there is two messages. First, going from 2 to 1. This means that GARP is a testable implication of rationality. If a choice dataset structure can be weakly rationalized by a rational preference relation, then you have as a testable implication that the dataset satisfies the GARP. So remember the previous lecture, I told you that WARP was a testable implication, right? Now I'm telling you that GARP is a testable implication. Okay, both are true, great. But you can see here that GARP being stronger than WARP means that we were missing testable implications, okay? So with the weak axiom, we didn't exhaust all implications of the rationality, okay? So there were further implications hidden, right? Do you understand? Now, important question. How do we know that we are not missing further implications of rationality? Is there anything beyond GARP that is implied by rationality? Do you understand the question? That's a very deep question, right? So we have testable implications. Now, how do we know we are done? How do we know there is nothing more than GARP? So that's a hard question.
Looking at the implication of GARP.
Yeah, exactly. So that's the other way. So basically, that's the other part of the theorem. Now, I have to show, in order to know that GARP is all that there is about rationality, I have to show that if a data set satisfies GARP, then I can construct, right, a complete and transitive preference relation that generates the data. And this is exactly the other way of the two-way street. One implies two, okay? And now we have what Irina said. This is the if and only if. And this allows me to conclude that GARP is the whole thing. So there is no further empirical implications of rationality. Do you understand? So there is nothing more beyond GARP. So GARP implies WARP, right? So hence we're fine on that side. And I know, and I'm sure now, that there is no deeper empirical implications of rationality beyond the generalized axiom of real preference. I'm done. That's all that there is to this theorem. Okay.
So if rationality implies GARP, then rationality implies WARP as well, right?
Yes, correct.
Great. Yeah, that's why I was asking last class, because I understood that that WARP implies that WARP is a necessary condition of rationalizability, but I didn't understand why it was a necessary condition for rationality as well. So yeah, okay, now I understand. Yeah. Okay, I get it.
So now, question. This is a question I asked in some exam. So imagine you have a data set that satisfies the weak axiom, right? Does it follow that the data set is rationalized? Can be rationalized by some complete transitive preference relation. So this data only satisfies the weak axiom. What's your answer?
Not necessarily.
Not necessarily, great. And basically, if you go deeper, basically, it's only the case if your data set is rich, right? That's a sufficient condition, right? So if your data set is rich and you have WARP, now it turns out that you are basically are back to GARP. Okay, so one take home for you, maybe I will make it part of the problem set, but I'm not sure. Try to prove that with rich data set, word implies GARP. Do you understand the question? So assume that the data set is rich. Now show to me that word implies GARP.
So in this data set, we have to have tripletons, right? Not just
Doubletons and
tripletons in order to make it rich. Okay.
Yes, doubletons, all the pairwise comparisons, and tripletons.
In order to prove that, you will need GARP if and only if rich dataset and warp.
So basically,
I would need to prove that.
You're saying that's correct, but the way I would write it is say assume the dataset is rich. Under that, word holds if and only if GARP holds, right? Or basically, you can also write the following are equivalent. This data set satisfies word. This data set satisfies GARP, right? Under the rich data set assumption. Agree?
Yeah.
Okay. So a lot of information, right? So it's a hard chapter. You know something now about rationality. Let's try to recap. So why do we care about this, first of all, right? So as I told you, right? So the first motivating idea for this chapter is basically these ideas of Samuelson, right? Paul Samuelson. So he basically said, look, we have to be able to learn preferences, right? In a way that is free from statements, right? So talk is cheap, right? So you know that people can say in a survey whatever. So we have in the previous lecture that people may, lie about what they want due to things such as social desirability. So it is desirable to have, some information from revealed preferences, right? From choices. Now, the issue from observing choices is that you don't want to observe, basically you cannot afford to observe all possible menus and see what people choose to know what to do. In real life, right, in Spotify, in the government, you will have only limited choice instances, right? Okay, so you won't have the full data set. So what do you want to do? You want to be able to learn preferences from limited data. Okay, this is the most important principle in econ, right? A lot of questions are about revealed preference, about what people want and learning what people want from choices, right? Now, this methodology is one methodology based under the paradigm of rationality, right? So we can learn preferences as long as people are rational. Now, but how do we know people are rational, right? If we don't observe their true preferences, how do we know? So when we go to the testable implications of rationality, right? And then we use the conditions of the weak axiom and the generalized axiom to be able to test whether the given data set comes from a rational individual, okay? Now, this means that it's compatible with rationality, right? So we have a principle in econ called as if. So basically, if you satisfy GARP, you behave as if you're rational, okay? I'm gonna expand on this point a little bit, but basically once you in a second, but let me finish my point here. So once you're done with testing rationality and your subject passes the test of rationality, namely GARP, now you can basically learn preferences from the subject, right? And now you can identify the preference of the subject, and now you can make predictions, right? And now you can make welfare analysis as well, okay? And we are not gonna do it right now, but we're gonna do it in the next chapter, okay? So prediction and welfare analysis are usually the final product of this, right? Okay? Yes, Martin?
So what are you using when preferences are not rational?
Okay. That's a great question. So when preferences are not rational, now welcome to my, my field of research, right? So basically we don't know yet, and that's a great thing. So it's a little bit, I'm gonna ask you the analogous question in a different field. So what do you do when we run out of oil? So how are we gonna run machines? So, well, we have electricity, nuclear energy, right? A lot of things. We have society settled on one alternative to our issue with oil? Not really, right? But it's exciting, right? So we're thinking about alternatives, right? So maybe electric cars and nuclear energy, great, right? So maybe there is a new source of energy later. That's amazing. The same is happening now in econ. If you are not rational, which there is a lot of evidence showing in many instances that people fail to be rational, mainly because of inattention, right? But there are only other issues. Then you need new tools, right? And we have some tools, right? So people have tried to create new tools, new models, alternatives to rationality. In fact, extensions of rationality. Because mainly, I think a lot of econ people are trying to expand rationality instead of scrapping it from the face of the earth, right? So we try to add features to rationality to be able to handle more cases, right? And yeah, we're going to see a chapter later on where we expand the utility maximization framework to one that you also have another layer called attention. So you're trying to maximize your utility, but you also have an attention that limits your knowledge and awareness of your alternatives. Hence, you are maximizing, but within the limits of your cognitive ability to be aware of the alternatives you have. Okay, we will come back to that later. I don't want to go too far right now, but it's a great question, Martin. If rationality fails, then you're in trouble, right? You're in trouble, and then you have to do more work, right? Okay. Now, funny thing, economics has been built on rationality, and for better or for worse, that has served us, well in some cases and badly in others, right? And but this is an empirical question. As any theory, we develop testable implications. Now, because we have testable implications, we can go to data and we can see whether in fact people are rational or not, right? And that's a cool thing. Hence, we can actually improve, because now we have a testable implication, we can get data, we can validate our model. If the model fails and we have too many data points saying your model is bad, then we finally acknowledge it and we improve the model, right? That's how science works, right? So testable implications means being falsifiable. You get a lot of data points telling you your model is bad. That's called an anomaly in the work of Popper. And then basically Kuhn, Morton Popper. So Kuhn in the theory of scientific revolution say you have a lot of anomalies, right? If you detect that, then what comes? A new paradigm, right? So a switch of paradigm. So we're here, we're just at the joint. It's a very exciting time, okay? So, but this is a class on the fundamentals. So you're just learning the thing we are learning, that there is some issues, right? But this is still
Professor,
useful.
So you think that now we're in the stage of modifying the paradigm?
Yeah, for sure. So one thing that basically, if you see the new papers, all of them have a layer of inattention or reference dependence or context dependence. And why is that? Mainly because now we have data, Irene. So before we didn't, right? So we just have a time series. So how do you know people are irrational or inattentive in a time series? You just have the consumption of a country in a trimester. That was our data 10 years ago, right? Now I have the consumption of all of you, right? When you were, shopping in Amazon, in Expedia, whatever. I see everything you did in a very long time. For instance, one of the data I use is called the Nielsen scanner data. That, is a marketing scanner. I got consumers that they sign up for gaining money. Actually, that's a good way to earn money, by the way, if you're a grad student. So you can download the Nielsen, and basically you earn money by shopping. So you go to your shopping, you go to the grocery store, and then you come back home and you scan with a device, right? A scanner, the barcodes, and that's what you do basically. And so that then people learn, in the marketing side, your choices, right? I know the barcode of every purchase you made, and every trip. You have to tell me to which store you went. So I went to Walmart, I went to Sobeys and whatever. I know the amount you pay, right? The barcode tells me all the features of the product. You tell me the price. And that information I now use. So now, for instance, I know how you purchased through years. There are people that remains in this scanner data for years. So I have basically 10 years worth of data, and the data has usually a frequency that is weekly, because people take usually weekly trips to Walmart, right? So this is super rich data, right? As opposed to what we have 10 years ago. So with this data, it's obvious that people are facing frictions, right? So one STLized fact in Nielsen data is that there are two types of consumers: people that spend a lot of time finding deals, right? So they spend a lot of time and a lot of trips finding the best possible deal of every product, right? So they go to, Meet Tuesday to get the best product on the state, right? And they go to Veggies Monday, and they, then they get the coupons, and then they get, all discounts. And then, these people invest a lot of search intensity, right, to get a good deal, right? So this, requires an extension of our models, right? Because this model, you take the prices given, but in reality, people are searching for prices, right? And are facing different prices because of the search intensity, right? And that's a famous extension of rationality. Another is, of course, attention to prices. I always tell this example. So for instance, I am, very distracted, I was a grad student. It's not that I have money, right? But so I went to the store, I saw, the white bread, right? So which I take, whatever is the first one, right? I go away. So when I went with my wife, she actually looked at the prices, right? And she knew the difference between option A and option B, and there was a difference of 20 cents, right? It's a lot, right? So then actually this makes a difference, but some people are very attentive to prices and sensitive to prices. Other people are less so, right? And of course, this changes with things. For instance, bread is not that expensive, so you can afford to do it, right? If you're buying insurance for your car, it's less likely that you're inattentive to the price itself, but you may you may suffer from issues such as complexity. So have you read the contracts in the insurances? For instance, if you bought a property insurance, so some people are super dedicated and they read everything. Most people say, oh, so my friend told me to get this, TD property insurance thing. I'm gonna buy it, right? And then actually they leave options on the table that are better off. So you dig out for a day another insurer, you will probably get a better deal. But most people just pick whatever someone told you, right? And that's an issue of complexity, right? It's so complex that people don't want to spend time learning which is the best alternative. So when you go to insurance data, you see people choosing first order stochastically dominated contracts. So there are things that are the worst in the market and people pick it, right? So why they do it? Because is it because they are not rational? Well, they try to maximize, but given their limit time, limit attention to complexity. So yeah, attention is super important. But as you see, it's so complex that we haven't settled in a general framework, right? But we're going to study this, and I'm going to explore here two options. So this is like the Tesla of behavioral eco, right? The rational inattention model, okay? Rational inattention, fancy name. We're going to see it at a time. But yeah, so great question, guys. Now, any other questions before I proceed? Else, I'm going to wrap up the chapter. No? Okay. Okay, guys. So let's do this half an hour. And let's go with chapter 5. So chapter 5 is a little bit more practical if you want. So we're going to get more specific in some details. But we're also we're going to get actually our hands there trying to write down models and utility functions. So this chapter is a little bit closer to what you learn in undergrad as well. But you can think of this as with utility functions, optimization, calculus, right? So those are the tools you need here. So less abstract order theory as before. But at the same time, right, is also a chapter that is going to connect with chapter 4, So we are not going to forget about guard and work. Just we're going to see a phase of work and guard in a different choice environment. So in particular, what I'm going to do in the consumer theory utility maximization chapter 3 in Mascolel, is to change and now for the first time be specific about the choice set I'm interested in. So instead of having an abstract choice set, I'm going to have now the Euclidean space of size L with the plus basically just positive bundles. So one thing I want to basically remind you is that let me share now my screen, my iPad quickly. Just give me 1 second so until I connect. Okay, I don't know, it's not working. Okay, so I cannot do it right now. So let me go back to the screen. iPad failed. I have to check it out. Can you see my links back? Okay. So yeah, so basically this is the Euclidean space. The Euclidean space is fundamentally telling you that you have fractional trading, right? So this is a classical plane that you have in two dimensions, right? For the two goods, and then basically you're choosing a bundle of goods. So, and in particular, instead of having general menus, here we're gonna have just linear budgets. So I need more notation, I need prices, and I need income. So the space of prices is just gonna be capital P, and it's gonna be a subset of the Euclidean space of size L. L is the number of alternatives, right? And then here we can have two pluses because prices are not gonna be allowed to be zero. And then I'm gonna have also the space of income, which is just, you know, numbers of different income that people have. Now, so remember that we introduced in the previous chapter the case of a demand correspondence, right? And this demand choice correspondence was super general. It mapped from the power set to the power set, right? So it was super abstract. Now we're gonna make it more specific, and we're gonna call it a demand correspondence as opposed to choice correspondence. In this particular case, our Rayleigh demand correspondence is a mapping from a linear budget. So it's not longer important to write down the power set, right? We're just gonna write it as a function of prices and income. So you give me a price and an income level. This will describe a choice set or a menu, which is a budget hyperplane. So hence I can write it directly as a mapping from prices and income to, of course, a subset of the power set. So namely, any consumption bundle or basket inside the XPW, right? Or the demand correspondence for the price P and the income W has to be that it satisfies the budget constraint. So if I multiply price, this is the notation for the transpose, right? And hence it's an inner product with X has to be less than equal than income. So
can I make a question about the notation? Very
sure,
quick.
sure.
What was the meaning of 2 power to X?
Yeah, so this is the power set, remember? So this is the collection of all subset of X. So this is just the collection of all subsets of the choice.
Okay, thanks a lot.
Yeah. Okay, so remember, this is kind of the black belt version of whatever you saw in undergrad. So instead of having just a demand function, right? What is a demand function? Who remembers? So basically it's a mapping that takes prices and income and gives you what?
Quantities, demanded quantity.
Yeah, well, it's called a demand quantity, demand basket, right? Which is this X vector that is of the Euclidean space of size M, right? So Martin is correct. Now, what is a demand correspondence? Well, is the analogous of the previous chapter. Basically, instead of having just one basket, right? We have a set of baskets, okay? Agree?
So it's like a vector, Professor?
The vector would be the output of the demand function. The demand correspondence, the image is a collection of vectors. In fact, is a set of vectors, okay? So Irina, basically what you're missing is that you're just looking at that element of the demand correspondence. A demand correspondence can have more than one vector, okay? Can have multiple vectors, okay? Okay, perfect. Yeah, we're gonna see examples. So I'm gonna give you an example in example 20, which is actually, let's do it now. So example 20, imagine I have two goods, right? So bread and butter, right? Two goods. Now I have two prices, P1, P2, and income is always a scalar, so W. So a demand correspondence now will be the following. I'm gonna describe it by cases. It's gonna be equal to X1. So remember there are two goods, right? So it's always a vector, but I'm gonna describe it entry-wise. So X1 of P1, P2, W is equal to income divided by P1. So basically this object is consuming the quantity of bread equal to the whole income divided by the price of bread, okay? So it's spending everything she has on bread, understood? And that happens whenever the price of bread is lower than the price of butter, okay? So maybe bread and butter is a bad example because a complement, you know, actually this is an example of perfect substitutes. So let's say bread and, I'm Latino, so I like arepas or tortillas, right? So bread and arepas, that's perfect substitutes for me. Maybe not for you, but for me it's perfect substitute. Okay, so bread and arepa. So now you have W divided by P1 if the price of the arepa is cheaper than the bread. So I say, I want some arepas. Now, now you actually, because this satisfies the budget constraint, what is the X2 at this price? Is 0, right? Because I'm already exhausting on the budget, okay? So this has to satisfy the budget constraint. Now, the other case is that the price of bread is equal to W divided by P2 whenever the price of bread is cheaper than the price of arepa, right? So I'm just buying the cheaper object now. And now the important thing, answering the question of Irina. So look at the case when prices are equal. So what happens if the price of bread and arepa are the same? What it happens to this particular guy? This guy doesn't know what to do, right? Hence the demand is a set. And the demand for arepa or bread basically is any point in the interval of 0 to W divided by the price of the item, okay? So this is a mathematical description where basically this person, because it's a perfect substitute, right, can pick any point in the interval, right? So remember
it's like
that.
linear, oh, sorry, it's like a linear combination? Is it the same association?
Mathematically,
kind of?
So you have to be careful, right? So it's true that it's a segment, right? So you can describe it as a linear combination, but you remember that mathematically we learned what was a choice correspondence in the previous class, right? So this choice correspondence was basically a set of choices that we call it the choosable set, right? So are things that the consumer plausibly can choose, right? Remember? So for instance, if I see this guy on Nielsen, and if truly arepa and bread are substitute for this guy, you will just see in every instance in the Nielsen, right? In every trip, he buying any quantity between 0 and W divided by the price of the quantity, right? So basically being choosing in any point here, right? Whenever the price of 1 is equal to price of 2, right? So this is mathematically is as a set. So the choice of this guy is a set. What it means is that theories are being lazy and they don't want to predict exactly what this guy is doing. So they are saying this guy can pick anything in this interval, right? Is a choosable set. Is anything between 0 and W over P1. That's where you can see the choices of this guy, okay? Now, I agree with Irina that she's worried because, for instance, let's say I'm hired by a consultant firm, right? I'm hired by Walmart and they want me to study the demand of bread and arepa, right? So now if I go and tell them, look, when prices are the same, anything goes, right? So are they gonna be happy? Not really, right? So they would like more information, like for instance, the probability of choice. And that's kind of the next level. So that's called a stochastic choice. But remember that I told you right now, we're not doing that. This is the 60s Mas-Colel version, right? Where Mas-Colel is able to tell you only that the perfect substitute guy can pick anything, right? Between 0 and what is affordable when prices are the same, because it's a perfect substitute case, right? So my best guess is the whole set, okay? Understood? Okay. Good. Okay, so now let's do something
Could
more.
be any other set, like a set that consists only of, for example, say 2 alternatives instead of this interval?
Whole interval. Yeah. So that's a great question, Martin. So in the previous chapter, yes. So the previous chapter was so general and so abstract that choice correspondence can have, for instance, 2 vectors, right? Here, instead, we have a continuum, right? We have basically, it's the whole section of the Euclidean space, right? When you project it to 1 dimension, is the whole segment, okay? So why, so in this particular world, in this particular chapter, turns out that all our demand correspondences will be what is called convex value. So it means that the image of the demand correspondence is a convex set. Okay, Martin? So if you have in this 2-dimensional case, it basically means that you will have either a segment that is fully connected, right? or a point. There is nothing in the middle, right? So for instance, your case, if you have two isolated points, it's ruled out because that's not a convex set. Okay, so that was a little bit a glimpse into the future. So don't fret, the rest of you. But basically, I will know eventually under the assumptions of this chapter, namely that my utility is going to be assumed to be quasi-concave, or for everyone that studied this in undergrad, a concave function, right? Which is the more popular friend of quasi-concavity. Assume it's a concave utility function. If you assume you have a concave utility function, the demand correspondence has to be a convex value. That means that the image or the collection of vectors that you have has to be a convex set. Okay, so is a segment a convex set? Yes. How do you know? Take 2 points in the segment, right? Do a linear combination, and then the linear combination will remain in the segment, obviously, because the segment is connected, right?
Okay.
Now, what Martin was describing is a counterexample. So this cannot happen in this chapter, but I will tell you why. So you don't know why. So he's asking if in this chapter we can have just two isolated points. So say, for instance, quantity 0 and quantity W divided by P1. That's not possible in this chapter because of the assumption of concavity that will come in a second. Okay, let's not run ahead of ourselves, but yeah, we have more structure in this chapter. So example 19 also to fix ideas. So observe using the notation of the previous chapter, how do we connect this demand correspondence here to the demand correspondence in the previous chapter? Well, basically, remember that you can, in the previous chapter, we have that the choice correspondence was a mapping from this capital B, right? The calligraphic B, the collection of menus, to the power set, right? Now, how do we map this previous framework in the previous lectures to the current framework? Now we define a budget correspondence. So what is a budget correspondence? It's a description, basically a mapping from prices and income to subset of X, okay? And fundamentally what we're gonna do is that the demand correspondence is gonna tell you that this is the set of alternatives such that X has to be, has to satisfy the budget constraint within equality. So this is describing the whole space, right, of alternative X, such that P times X is less than or equal than W. And in fact, right, we know that the choice correspondence here is only allows positive quantities, right? So this is also imposing the fact that the X's are non-negative, okay? So remember that this is a full description of the budget set. Now, look at my demand correspondence. So my demand correspondence is in fact a composition of the choice correspondence that you learned in chapter 4 with the budget correspondence, right? And now basically what this demand correspondence is doing this, is transporting a price and an income level through the budget correspondence to the collection of menus. And then through the choice correspondence is basically mapping the menu, which is a budget set in this case, to the power set, okay? So this is basically, I know it's a lot of symbols, but you have to sit down, later on and try to really internalize this to make the connection of chapter 5 to chapter 4. We're talking about the same object, right? We're just using a shortcut because instead of having any kind of menus, we just allow budget planes, okay? Budget hyperplanes, sorry. Any question here? It's fine to have questions. There's a lot of symbols and change of.
Yeah, I have a question. When I pass for all these, arrows, and I finish with the power set, that power set contains only the available for given my budget possible alternatives. Yeah. That is the reason because you are passing for all those arrows, I am saying in that way, in order to only have available the available
that's correct.
That
that's
you
correct.
can acquire with your budget.
That's correct. Remember that as Juan is saying. So here we're mapping, right, from a vector, which is a price, right, of the size of the number of goods and income, This is transformed by the first arrow to a budget hyperplane, right? So budget is a menu. It's a collection of alternatives that is given to the consumer, right? So this is the budget constraint. The first arrow is just converting price and income into your budget, okay? The second arrow is the arrow of choice, right? Given the menu, the consumer uses the preferences that she has, and then she picks something from what is affordable. So the final product, you know, is basically something that is affordable, so inside the budget, right? But is also preferred, right? In some sense, so the subject will pick it, okay? So there's two processes going on here, okay?
So it's it's on the budget restriction. If I imagine a linear, for example, is on the is affordable and is optimizing.
Yes,
the agent is optimizing.
That's going to happen eventually, right? But right now we're allowing at this stage of generality. And it's always, remember that in these chapters, we always start from something super general, right? And then essentially we're going to converge to the natural thing that you learned from previous classes, right? So essentially at the very end of this chapter, we're going to realize that in fact, choices are not going to be living inside the budget, but rather are going to live in the frontier, right? They're going to be picked at the very upper part because you want the best, right? And usually the best is the thing that is going to exhaust your budget, right? And this is coming from an assumption called monotonicity or local association, but we're going to get there. At this stage, we are not there yet. So you can actually pick here anything inside the budget. It can actually be not in the frontier. It can be inside.
Okay.
At this stage. Okay. So great. So I'm going to need some mathematical definitions in order to introduce some concepts in the chapter. If you have access to Maskell, Wilson, and Grimm, they have this mathematical appendix. So they have a small discretion on correspondences, and they introduce some of these concepts there a little bit more in depth. So if you want to go over that, also you also did a little bit with Maria, and you're gonna do it in general in the math class, right? So I'm gonna just use these definitions. I'm not gonna go deep into the playing with the definitions. That's not in this class, right? So you have to complement that if you are a little bit lost, but I'm gonna try to explain what is needed here. The first thing is a notion of continuity in the world of correspondences, okay? So what does it mean basically to be continuous? Well, for functions, everyone at this stage should know what is a continuous function, right? So if you allow for some topology and you basically allow, you have some notion of, basically you are able to have sequences. Imagine you have a sequence of prices, right? Pn, Wn, and this sequence converges to some limit, Pw. Now, if that's the case, it has to be that in the world of the man functions, I highlight function, so single value function. X of Pn Wn, the image, right, which here is just a point, will converge to XPW, right? This is a classical sequential definition of continuity, right? Everyone agrees? So remember, you can also write it down with the epsilon delta, you know, same deal. I'm just writing the version that is more shortcut in Maskell, right? Using these sequences and limits. Again, I'm being informal, because I haven't defined a topology, I haven't done anything really. There is some way to study convergence of sequence, you know, with some topology, and now it can be the natural topology induced by the Euclidean norm if you want, whatever you want, doesn't matter. Imagine there is a PNWN converging to PW. It has to be that the demand function, the image of the demand function also converges. That's continuity, right? Now, what is continuity for correspondences? Now, correspondences, remember, are not longer single value, are set value, right? So we have a set. So as we have in the example 19, in the example 20, sorry. So how do we know something like this converges, right? And how do we know if they are continuous or not? So the first notion I'm going to introduce is called continuity of correspondences, right? Which is a little bit too strong for what we need, and then we're going to weaken it a bit, but let's learn it. So continuity for correspondence. We say the map the map or the function, the demand correspondence is closed. So I'm going to use map interchangeably with function with correspondence. Sorry, so map or a correspondence is the same. It's closed. The demand, the graph of the correspondence is closed, and basically, and you have also something called apparent continuity that I'm going to define it in a second. So let X be basically a demand correspondence, as we did in example 20, sorry. Now take a sequence of prices. That's the same as in the case of functions. So Pn, Wn, and let them converge to a new vector, Pw. Now, because the demand correspondence is set value, you can no longer just check the sequence of the single value, right? You have to select items inside the set. Namely, select xn's that belong to the image of the correspondence x at the point Pn, Wn. So remember, let's go to example 20. From this interval, I pick one point, say 0, right? That's what I'm saying. Do you understand? Okay. So from this interval, I get 0. That's what I'm saying here. This is this xn I am taking here. Okay. 1 point from the image. Now, and basically what I require is that this selection of points converges to some x. Yeah. If that happens, it has to be that the x, that is the limit of the sequence, right, belongs to the xpw. Okay. And that's a continuous correspondence. Now, again, the only thing that this is doing is expanding the notion of continuity, right? But for set value objects. So the trick now is that instead of just considering one single value, always we select a collection of singletons, right, from the images of the set value correspondence, right? And then this thing has to converge to a point, and whatever the point of convergence is, it has to be that the point in the limit belongs to the demand correspondence evaluated at the limit point in the input side, okay, at the PW. So, you know, it's a lot of words, but it's very simple. It's the analogous definition of the demand function, but for correspondences. And this gives us a notion of continuity. What do we need? These things, and then we're gonna weaken it up to apparent continuity a little bit later. But basically we need it because when you are maximizing a utility function, continuity is very handy, very useful for being able to apply some theorems such that we are able to conclude that there is a maximizer. So in other words, a continuity is a technical condition that will help us in our endeavor of writing down models of behavior. Okay. Continuity is not really important behaviorally, right? So you're never going to be able to test continuity as you test transitivity, right? Or GARP. So continuity in that sense is not behaviorally important, but it's mathematically important to close our models to make it mathematically sound. So I always want to separate this kind of definitions and technicalities, right? So continuity is not important in the sense that I could never test if some of you have continuous utilities or continuous demands. Do you understand why? So in order to test continuity in real life using experiments, I will need to run infinite experiments, right? And be able to take limits, right? That I can never do. So in that sense, continuity is not important because it's purely technical. It only lives in the math world, right? At the same time, right, because we are writing down models, one key property of models is that they are internally consistent, right? That the models are not contradictory, right? So you want models to be well-behaved. And one key feature of a well-behaved model of consumption is that the model produces a prediction out of a budget, okay? And continuity is going to be important as a technical part that is able to allow us to have always existence with other conditions, okay? So in that sense, continuity is important. So remember that, right? So don't get scared by this technicality. It's something we need to do in order to have internally consistent models, right? But it's not a behavioral object. So you have to get intuition why people are continuous or not. But people are not continuous. We don't know if they are. Maybe you are. I have no idea. I can never run an infinite experiment, right? That is a technical thing. Okay. So understand those dimensions and keep going. Now, important thing, right? we're gonna say that a correspondence X is compact value if XPW is a compact set, right? For all PW. Now, time to use your real analysis. What is a compact set?
A set that's closed and bounded.
When you are constraining your attention to the Euclidean space, compactness is equal to being closed and bounded, right? In general, right, we know that compactness and close and boundedness, right? You know, it depends on the topology and so on. Basically, being compact means that you have finitely many covers and so on, but there's different levels. The definition that Amal is telling us is great. So closed and bounded, the sequential analogous of that basically means that you basically can take if you take a sequence xn and it converges to x has to belong there, right? So that basically means close. And here we're assuming also that it's bounded, right? So in fact, here we should say close, right? And also bounded. To be clear, that is bounded, you have to ask this explicitly. Okay, so close and bounded, that's what is called compact value. So the image of this correspondence is close and bounded. So is example 20 a demand correspondence that is compact value? Yes or no?
Yes.
Yes, why?
Because all of the solutions are bounded by the constraint, right? That's how I see it.
That's bounded, right? And are they close? So the first part.
They're closed because you can take values on the boundary. It's not like there's an exact point that's the cutoff between both. I mean, we explained this. So yeah.
This is described by cases, right? So all cases are either a singleton, right? Which is a single point is close, right? Or is a closed segment, right? So in all cases it's closed, okay, agree? So what will be a counterexample? So I make this open, right? Semi-open. So this will be a counterexample, right? Agree? This is not closed anymore. Okay. So this is a compact value. And what is convex value? So we say element correspondence is convex value. If you take any 2 points in the image, and then you take a linear combination of the 2 points, Z and Y, and the linear combination falls inside the image of the choice correspondence, right? That's basically the definition of a convex value demand correspondent. Is example 20 convex value? Yes or no?
No.
No, it is convex value, because remember that it is either a singleton or a closed interval, right? Connected, in fact. So when you have a single point, you are convex by default, right? So a single point is convex. If you apply the definition, it holds in a vacuous way, okay? Because you can never take a second alternative and do a linear combination. There is only 1 point, right? So it holds vacuously. So single images are convex, and then the interval here is a convex set. Now, what is an example of a non-convex interval? For instance, this one. Say you have 1/2, right? And then you have this thing, 2/3, 1. Then I take the union. You see this interval here I just wrote, right? This thing is not convex, okay? Do you see why? There is a hole in the middle, right? So if I take, for instance, the convex combination of 1/2 and 2/3, I'm gonna end up with some point in that is not there, okay? Do you understand? This is non-convex, okay? Disconnected interval, okay? Great, so turns out that example 20 actually is compact value and convex value. Okay, this will become important in a second. All of these are technicalities, but again, they will be important because we want to make our model internally consistent, right? It's not really about these being properties that are important for behavior. They are not, but they are important to make our model mathematically sound, okay? And that's gonna be also an objective of this chapter. So I have 5 minutes, so I'm gonna stop there. Please do read remember that you can have Mascolel also, the PDF version, you know, just don't tell me how you got it. There is no ebook, right? So you understand. You've got the physical one, whatever, you know, there is an appendix there, the mathematical appendix. The authors go into deeper definitions for the demand correspondences. So if you're having trouble understanding the math of the demand correspondences, please refer to the Mascolel, Winston and Green mathematical chapter. Also the books that you're using in the math class is also, a big part of that class is dealing with these demand correspondences, right? In general, correspondences, right? This is the new mathematical object we need. So try to get acquainted with it. It's nothing crazy, but you know, if you are having, you know, some jump from demand functions to demand correspondences, try to do it now. You're gonna use it for the next year, okay? So any questions here? No? Okay. So let me stop the recording, and I'm gonna stop sharing and also stop the recording, and then